Now we're ready to start in on the failures of the Bohr theory and the contributions of Ernst Schrodinger. And keep in mind now, we're going to be continuing to develop our model as we go through all of this. It's about this time that my students start really pulling their hair out. They're so confused. How can they think of the electron as a particle and as a wave? Well, look at this. This is a standing wave. But instead of expressing it linearly, let's say that this is the wave of A expressed as an electron. Let's take this and let's put it around a nucleus. Now in this case, n is 5. Why? Because the circumference of that orbit is sufficient to handle 5 complete wavelengths. What about this? In this case, n is 4, because the circumference of that orbit can handle 4 complete wavelengths. Well, what about a case in which n is between 4 and 5? Maybe it's 4.5. Folks, you can't have that. You would get destructive interference because you cannot accommodate a whole number of wavelengths here. This is a method that helped scientists early on think about the correlation between orbits and waves. Although we're describing it this way, this does not mean that electrons travel in circular orbits. Let's go on with our development of this concept. And into this swarm of information and ideas and activity comes Ernst Schrodinger. Now his proposal incorporates the concept of allowed states. Bohr was saying that the electron is allowed to be in orbits 1, 2, 3, 4, 5, etc. Those are allowed states. So Schrodinger proposed using the concept of allowed states, but incorporated into that the wave nature of the electron. And instead of talking about a particular position of the electron or something of that type, he talked about a probability of finding an electron at some given distance from the nucleus, with a high degree of probability, if you will. So now we come to what we choose to call the modern atom. Now let's look at some terms that were generated by Schrodinger. The first term we want to look at is wave function. A wave function is a mathematical expression. It's a mathematical expression that describes allowed states for an electron. That is a wave function. Not orbits, but orbitals. An orbital is, if you will, for our purposes, it's another term for wave function. Now, Schrodinger proposed to characterize electrons using 3 variables. 3 variables that together would satisfy the mathematical expression. A 4th value was added later. Here are the values. N is the principal quantum number. These are quantum numbers now, whose use will solve the wave equation. N is principal. L is azimuthal. M sub L is the magnetic quantum number. And the one that was added later, those are the ones that were added by Schrodinger. The one that was added later was the spin quantum number, N sub S. Remember, these 3 are from the Schrodinger equation, and this is the one that was added later. Well, now, let's look at these in a little greater detail. The principal quantum number n. Remember Bohr's idea? Remember the idea that n can be any whole number, 1, 2, 3, 4, 5, and so forth? This is referred to as a shell in the modern atom. It is a shell. And what the shell does is describes the distance from the nucleus where an electron is expected to be found with a very high probability, of a probability really greater than 90%. In other words, more than 90 times out of 100, if you look here, you will find an electron. Let me give you an analogy I like to use. Suppose you have seen something interesting in all of this tree area, this forest area around this lake. And it just flashes periodically. And you've told people about it, and they say, well, we want to see it for ourselves. So you direct them to this area, and you say, here's a picture. And within a 90% probability, you're going to find it here. I see it here, I see it here, I see it here, I see it here, 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 and on and on. What is it? That's the question. What is it? I don't know what it is, but I do know that as I look for it, I'm going to find it 90% of the time in here. So that with that piece of knowledge, people can come back and follow up on your work and see, yes, we see this, and then they can study what it is. Let's look at L, the azimuthal quantum number. Now, L can be any whole number value from 0 to n minus 1. N minus 1. If n is 3, then L can be 0 or 1 or 2. If n is 1, then L can be and only be 0. It is often referred to as a subshell. And what it does is it describes the shape of that 90% probability volume where we expect to be able to find an electron. It describes the shape. This is called the azimuthal quantum number. M sub L is the magnetic quantum number. N sub L may have any whole number value from minus L through 0 to plus L. If L is 2, M sub L can be minus 2, minus 1, 0, plus 1, plus 2. Get the idea? If L is 1, M can be minus 1, 0, or plus 1. Got it? Okay. And what it gives us is the number of orbitals in a subshell. The number of orbitals. Now, we're not talking about orbits. We're talking about orbitals, 90% probability volumes. It describes the spatial orientation of those orbitals with respect to the standard 3 axes, x, y, and z. The spin quantum number is designated as m sub s. Now, m sub s may have one of two values. It may be plus a half or it may be minus a half. And we will explain this in much greater detail when we get to a section a little later on in this unit. This quantum number permits pairing of electrons. You can pair a plus 1/2 electron with a negative 1/2 electron. And as I told you, that will be clearer later. But it was added as an afterthought because it was describing a particle property of electrons. Now, m sub s is sometimes designated as just s. But understand, they're the same thing. Well, now, let's build a table and show how these quantum numbers are related to each other. Here's a basic table for us to use. Now, I have already filled in the values of n. Let's start with the case for n is 1 and look at L. If n is 1, what is L? Well, do you recall that L can be anything from 0 to n minus 1? Well, n is 1 and 1 minus 1 is 0. Therefore, L must be 0. And m sub L? Remember, m sub L can be anything from minus L through 0 to plus L, but L is 0. So what is m? 0. Yeah. And spin? Well, we have two choices on spin. It can either be plus a half or minus a half. Now, look at this. How many electrons can we describe such that each electron has its own unique set of quantum numbers? You can repeat some of the numbers, but you can't repeat them all. In other words, they have got to be at least one quantum number different. Well, the first electron there could have the quantum numbers 1 for n, 0 for L, 0 for m sub L, with a plus 1/2 spin. And another one could have 1 for n, 0 for L, 0 for m sub L, and minus 1/2 for the spin. And I don't see any other possibilities. So the number of electrons then that I see for the first level, n is 1, will be 2 electrons. All right, let's go to the second energy level. The second level when n is 2. When n is 2, L can be 0 or L can be 1. Remember, L can be anything from 0 to n minus 1. Okay. Let's take the case of L is 0 first. If L is 0, what must m sub L be? And the answer is 0. And spin, well, spin is always plus 1/2 or minus 1/2. So what is the total number of electrons that we can describe when we have n is 2, L is 0, and m sub L is 0, and the spin is plus or minus 1/2? And the answer is we can describe 2 electrons. Okay, let's go now to the case for under n is 2, the case for L is 1. If L is 1, what is m? Well, do you recall that m can be anything from minus L through 0 to plus L? So m can be minus 1, 0, or plus 1. And the spin, we've already said, can either be plus 1/2 or minus 1/2. So if n is 2 and L is 1 and m is minus 1 or 0 or plus 1, and the spin is either plus 1/2 or minus 1/2, how many possible combinations of quantum numbers can you have there that are unique? Think it through. And the answer is 6. So this gives us a total of how many electrons that we can describe for the second energy level. And the answer is 8, a total of 8. All right, now let's go to the third energy level. In the third energy level, L can be what? Well, it can be 0 or 1. Is there another value? It could be 2. All right, let's take the case for n is 3 and L is 0. What is m sub L? The answer is 0. And spin, plus 1/2 or minus 1/2. So with 3, 0, 0, plus 1/2 or minus 1/2, how many electrons can we describe? Yeah, you got it. It's 2. All right, now let's look at the case for n is 3 and L is 1. If L is 1, what is m sub L? Well, it can be minus 1, 0, or plus 1. All right, if n is 3 and L is 1, and m sub L can either be minus 1 or 0 or plus 1, and the spin is either plus 1/2 or minus 1/2, how many electrons can we describe? That's right, and you got it, 6. All right, getting the idea? Let's go to the case for n is 3 and L is 2. If L be 2, what be m sub L? And the answer is -2, -1, 0, plus 1, or plus 2. 5 different choices there. How many different choices for spin? 2 different choices, plus 1/2 or minus 1/2. So how many electrons could we possibly have coming out of 3, 2, and that array of choices for m sub L, and the 2 choices for m sub S? Well, multiply it this way. There's 1 choice for n. There's 1 choice for L. There are 5 choices for m sub L, and 2 choices for m sub S. So 1 times 1 times 5 times 2 is 10, giving us a total of 18 electrons for the third energy level. All right, let's look at 4. If n be 4, what be L? And the answer is it can be 0, 1, 2, 3. Yeah. All right, if n is 4 and L is 0, what is m? Right, it's 0. And the spin, plus or minus a half. So how many electrons can you describe from there? And the answer is 2. Okay, go to n is 4 and L is 1. Then what is m sub L? And the answer is minus 1, 0, or plus 1. And using that combination, how many electrons can you describe? And the answer is 6. Are you seeing a pattern? For n is 4 and L is 2, what can m sub L be? Minus 2, minus 1, 0, plus 1, plus 2. And you have two choices for spin. You can describe how many electrons. 10. That's right. Okay, let's go to n is 4 and L is 3. M can be what? M sub L. Well, it can be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. And the spin is plus a half or minus a half. So the number of electrons that can be described is 14. And that gives us a total of how many in the fourth energy level? And the answer is 32. Now, we could go on. We could go to the fifth energy level. But if we did, for the electrons in the atoms that exist to date, that we know of to date, the fifth energy level is like the fourth. The sixth is like the third. And the seventh is like the second. So now you know the whole array, but expect it to change, because it's very possible that we're going to find some elements with sufficient numbers of electrons to take us beyond what I have just shown you. And we will deal with those when the time comes. Now we have all of these values for the quantum numbers. But what do those quantum numbers tell us about the size of the energy levels of the electrons, the shape within those energy levels, and the orientations of those shapes? Now you have to remember, folks, we're dealing with a model. We're not talking about the actual shape and size of atoms. We're talking about with a model that we have developed that tries to explain and allow us to make predictions about the behavior of atoms. This model describes the high probability volumes for finding electrons. It describes areas where we might find them. It says absolutely nothing about how those electrons are going to behave. It really says nothing about what those electrons are, except it does suggest that they have wave character and particle character. Well, let's model. Here's our basic table. Let's begin with L. You will notice that L has a value of 0 in each one of the levels. Let's start with that 0 then. We're going to designate that 0 as S, and we will talk in just a few minutes about what S stands for. But you see that we have S when n is 1, when n is 2, when n is 3, when n is 4, and we can have S when n is 5 and 6 and 7. There's another value for L, and it starts in the second level when n is 2 and occurs thereafter, or can occur thereafter. And when we have L with a value of 1, we give that the designation of P, and we will talk about what the letter P stands for a little later. But you will see that we have that in the second level, the third, the fourth, and can have it in the fifth, and so on. Notice in the third level we have another new shape. It's designated with the number 2. Instead of 2, we're going to use the D, and I'll explain what D means in just a few minutes. But D can appear in the third, and in the fourth, the fifth, and so on. The last shape that we're going to mention occurs in the fourth level, and it is designated with an F. Now, let's talk about what these things might stand for. And oh yes, F can appear in the fifth and so forth. If we were to have more electrons in an atom than we currently have, we might have to add to this list. But for right now, this covers the atoms known to date. Let's go on. The S shape is named for the sharp line in the emission spectrum, and it has a shape that we designate as being spherical. S does not stand for spherical now, it stands for sharp. But you notice that if we were to plot S against the three axes, X, Y, and Z, it would have the same value on all 3 points as it intersects the axes. So we say it has one orientation with respect to the X, Y, and Z axes. But where in that S shape is the electron located? Well, let's do a plot. Let's plot the radius of this sphere, beginning at the nucleus, and let's plot that against radial probability. In other words, for us, the likelihood of finding an electron at that distance. Now, as we start at the nucleus and move out, this is the kind of plot that we get. And do you see then that the probability of finding an electron is greatest at this point right here, which is about this distance from the nucleus? Then probably that is somewhere in this area of the S shape. How do the S shapes compare when n is 1, 2, 3, and so forth? Well, let's let this representation be our 1s. Then the 2s is out here, further away. And the 3s? Well, the 3s will be yet further out. The question is, what are these areas? These areas are called nodes. And those areas are volumes, actually, where the probability of finding an S electron is very, very low. But let's look at something called the penetration effect of the 2s orbitals. When we look at a radial probability plot of the 2s electrons, we find it looks something like this. Now, the probable distance that we're going to find the 2s electrons is here. This is the greatest probability, about this far from the nucleus. But the question is, what is this? This, we think, is due to penetration, or the penetration effect. In other words, there is a probability, fairly small, that the 2s electrons will exist in this volume much closer to the nucleus, for a certain portion of the time, perhaps. In any case, that results in a very, very strong attraction, or possibly it is the result of a very strong attraction between the s electrons and the nucleus. Here is a question for you to think about. What would a penetration effect plot for 3s electrons look like? What about 4s electrons? That's a concept you need to think about. Now let's look at the P shape. When we talk about the P shape, it is named for the principal line in the line emission spectrum. And this is a representation of what its shape might be. Now again, we are looking at probabilities of finding an electron. We're not saying what the electron is, what it looks like, how it's moving. We're just saying, hey, it's in here, with a probability of 90% or better. There are 3 orientations. These 3 orientations are on the x-axis, the y-axis, and the z-axis. So 3 orientations, the p sub x, the p sub y, and the p sub z. These 3 p orbitals are degenerate orbitals. What does that mean? That means they are of equal energy. So the px, the py, and the pz are of equal energy. Think about it this way. You might say, how do I know which to designate the x, y, and the z? Suppose we say that we're putting in electrons one right after the other. The first electron then going into the p orbitals will go in on the px. That's what we will designate as the px. That's one way to look at it. The D shape. The D shape stands for the diffuse line in the line emission spectrum. Now let's look at the 5 orientations of the D and label the appropriate axes. The first one on the top left is oriented with respect to the x and y axes. The next one is oriented with respect to the z and the y axes. I'm having to use them flat right now. I will attempt to rotate them in a moment. This one is rotated with respect to the x and z axis. This one is oriented with respect to the x and y axis, but note how it is different from the one above it and to the left that is also oriented with respect to the x and y axis. And then we have this one that is oriented with respect to the x and z axis, looking considerably different from the other one that is oriented with regard to the x and z axis. To give them their appropriate names, starting with the one on the upper left, that is the d sub xy. This is the d sub yz. The next one, yes, you can imagine, it's the d sub xz. The bottom left is the d sub x squared minus y squared. And then we have the d sub z squared. But let's not remember them like that. Let's think of them as the d sub 1, the d sub 2, the d sub 3, the d sub 4, and the d sub 5. Now I'm rotating it. Notice that the d sub yz should be oriented something like this, but remember it is a three-dimensional shape. And this one should be oriented something like this, but again notice that it is a three-dimensional shape. You get the idea? Now superimpose all of those about the nucleus and you begin to get the idea of the complexity. For our purposes, these 5 orbitals are degenerate orbitals. They have approximately the same energy. As you go on in your study of chemistry, however, you will learn to differentiate among them more acutely than we have done here. The F shape. The F shape stands for the fundamental line in the line emission spectrum. And you should note that there are 7 orientations, all of which are degenerate. Now, I'm not going to go into a lengthy description of this. It's very complex. But let me tell you that there are a lot of resources out there on the internet for these. And here are several examples. So you might go to these to find other interesting ways of explaining and diagramming and graphing these things. And you should particularly pay attention to this last one right here, which is a very graphic drum membrane model that you very, very well may find interesting. As you try to make sense of all of these different ideas in this evolving concept of the atom, it would be a good time for you to go have a look at the Schrodinger cat paradox. I've given you the site here as the Wikipedia on the World Wide Web, but there are many, many other places that you can read about this, and you really should. Meanwhile, this is a good stopping point for us, and in the next lecture we will start the Aufbau process. A better way to teach and learn chemistry.